We've introduced the concept of resistance and how it restricts the flow of current. We're now going to have a look at the factors that affect resistance, and to do that we're going to start off first of all by looking at a water analogy. The reason why we're doing this is that it's a little bit easier to make sense of what would happen with flowing water than it is with moving charges. So we'll start with that context and then we'll move across into the concept of a resistor once we've dealt with this scenario. So the situation that we're dealing with, imagine we have two pipes that are going to be connected, and the way that they have to be connected using the materials available is using a narrower pipe between the two of them. So we have this sort of situation occurring. So you can imagine then we've got, if we had water flowing down through that pipe, it's going to get to this narrower section of pipe, and that's going to make it harder for the water to then flow through. Imagine we wanted to make it as easy as possible for the water to flow through that pipe. There are some things that we could change about that pipe in the middle in order to make the flow of water easier. The first is that we could make that pipe wider, and the wider that connecting pipe is, the easier it is for water to flow through, because there's a greater cross-sectional area for the water to fill up, and so much more water can move through. So the wider the pipe, the more water that can flow through. So there's the first property that we can change about that connecting pipe. The second would be to change the length. So in this case it might be something like using another section of pipe that we can join in here first, so that we extend this length a bit further so that it comes out to here somewhere. And therefore we only have to use a shorter section of the connecting pipe. If we have a longer connecting pipe, that's going to make it harder again. So the longer it is, the longer it's going to take for water to flow through. Now the third thing is a little bit silly in this context, but we'll go with it. If there was some debris inside the pipe, that's going to make it harder for water to flow through as well. So the material that's inside the pipe is going to have an effect on how fast the water can flow. So if it was clogged with debris, the slower the water will flow. So like I say, that's an analogy that we're using to help make sense of resistance and the factors that affect resistance. So this connecting pipe is an analogy for a resistor. We can look at the quantities that affect a resistor in much the same way. We'll just need to consider it in terms of electrons flowing through a conductor. And so we can make a direct comparison between them. So the first is that the greater the cross-sectional area of a resistor, so in other words, the wider it is, the easier it is for charge to flow. And so the easier it is for current to be flowing. So that means that with charge carriers moving through a conductor like that, with a wider cross-sectional area, it just means that those charge carriers can space themselves out more easily. They can move through much more effectively, and means that we can have more current flowing through. So the relationship that we can identify there is that resistance is inversely proportional to the area. So as area increases, it becomes easier for charges to flow through, and so R is inversely proportional to area. The second one is about the length, and in this case it's more about thinking of how much matter the charge carriers have to move through. So as it gets longer, there are more atoms the charge carriers have to move past, and if there are more atoms for them to move past, it means that it's going to take longer because there's more friction between them, more resistance to that motion. If we have a longer resistor, that means then that the resistance is directly proportional to L. So the longer the resistor, the greater the resistance. Finally, the type of material that's used. So this is the pipe being clogged with debris. If we have an empty pipe, there's an easy flow of water through it. If we have a clogged pipe, it means that the flow of water is much slower. The same thing applies to the type of substance for a resistor. So there are some substances that allow charge to move through very easily, and there are other substances that make it much harder for charges to move through. And the reasons why it becomes harder is to do with the structure of the material itself. So that could be things like the density of the atoms, how closely spaced they are, also the type of bonding that's involved, the arrangement of the atoms in the lattice that they're in. So a lot of different factors can affect it, but ultimately the type of substance can have a significant impact on the resistance as well. And so that proportional relationship is that R is proportional to rho. That's a Greek letter rho. Looks like a P, but it's a little bit of a curly P. Now, if we combine those relationships, we can calculate what the resistance is going to be. And it's literally just a matter of taking all of those three relationships and joining them together. We have the equation then that R is equal to rho L on A. And in that equation, R is the resistance in ohms. L is the length of the resistor in meters. A is the cross-sectional area, and left rho till last because we need to just say a little bit more about it. And cross-sectional area, I should mention, is in square meters. Rho is resistivity, and the units are ohm meters. Now, the idea of resistivity is that it's a property of the substance itself. So it's not the resistance. So be careful here that you know the difference between resistivity and resistance. So resistance is the property of the component. Resistivity is the property of the substance from which a resistor is made. So it doesn't incorporate the dimensions, it only incorporates the substance and all of those other factors I mentioned in terms of the density, the type of bonding, and so on and so forth. So it's the property of the substance that restricts current flowing through it. And in order to calculate it, we're going to take that equation above. You'll notice I didn't highlight that equation, it's not in the data booklet. Instead, this equation is, so the resistivity is equal to RA over L. So that's just a rearrangement of that equation above, but that's the one that's in the data booklet that you need to be aware of. So in this context, to calculate the resistivity, you'd need to know the resistance first. Usually you'd be able to look up the resistivity of different substances such as copper or silver or aluminium, whatever they may be, or even semiconductors like silicon, and even insulators like glass, rubber, and those sorts of things as well. But ultimately, in the data booklet, that's the equation that you need to know.